Imagine cooling your home with a rock. No fan, no compressor, no traditional refrigerant. It sounds impossible, yet one unusual mineral sparked decades of research and convinced engineers there might be a completely different way to keep buildings cool. So why don't we see zeolite cooling systems in our homes today? Was the technology flawed, or did something else prevent it from becoming mainstream? Let me know where you're watching from in the comments. Then join me as we uncover the forgotten story of zeolite cooling and discover what really happened behind this remarkable idea. To understand why zeolite cooling faded from view, we first need to understand what zeolite actually is. At first glance, it doesn't look special. It's a light-colored mineral found in nature and also made in laboratories. Nothing about its appearance suggests it could help cool a building. The secret is hidden deep inside. Millions of tiny pores riddle the material, so small that you can't see them without powerful microscopes. Together, those tiny spaces create an enormous surface area. That unusual structure allows zeolite to interact with water vapor in a very different way from ordinary stone. Most air conditioners depend on compressors and refrigerants. They force chemicals through a cycle that moves heat from indoors to outdoors. This mineral follows a completely different path. No spinning compressor, no traditional refrigerant. Instead, it works through a process called adsorption. Adsorption sounds complicated, but the basic idea is simple. Water molecules stick to the surface inside the material's tiny pores. As that happens, heat is released. Later, when it's heated, those water molecules leave the pores. That step stores energy inside the system and prepares it for another cooling cycle. Think of it like a sponge. A sponge soaks up water into empty spaces. Zeolite doesn't absorb water the same way, but it attracts water molecules onto its internal surfaces. That small difference changes everything. It creates a repeating cycle that engineers can use to move heat without relying on the same equipment found inside conventional air conditioners. This discovery wasn't new. Scientists had known about zeolite unusual behavior for decades. As energy prices rose and concerns about electricity consumption grew, researchers began asking an important question. Could this natural material become the foundation of a cleaner cooling system? The idea made sense. Sunlight could provide the heat needed to regenerate the mineral after each cycle. During hot sunny days, when cooling demand is usually highest, solar energy is also abundant. Instead of using large amounts of electricity to power compressors, a system could use heat from the sun to keep the cooling process going. Researchers around the world took notice. Universities studied adsorption cooling. Engineers built experimental systems. Companies explored new designs that combined zeolite with water to create environmentally friendly cooling units. The goal wasn't just lower electricity bills. It was reducing dependence on refrigerants that can contribute to environmental problems if they leak into the atmosphere. On paper, the advantages looked impressive. Zeolite itself is stable. It doesn't wear out quickly. Water is safe, widely available, and inexpensive. The system could operate quietly because there were far fewer moving parts than in a traditional air conditioner. Every new experiment suggested the concept deserved serious attention. Everything seemed to be pointing toward a breakthrough. Researchers had discovered a material that was reliable, abundant, and capable of producing cooling through an entirely different approach. For a moment, it looked as though homes of the future might depend less on compressors and more on clever chemistry. Yet despite all that promise, something stood between the laboratory and everyday life. The obstacle didn't stop researchers from trying. Instead, it pushed them to build real systems and see whether the technology could perform outside the laboratory. During the late 20th century, universities, research centers, and private companies began testing adsorption cooling in offices, hospitals, factories, and homes. The question was no longer whether the science worked. It was whether it could work every day. Timing seemed to be on their side. Electricity demand for air conditioning was climbing across the world. Hotter summers placed greater pressure on power grids, while growing environmental concerns encouraged engineers to search for cleaner alternatives. Zeolite appeared to offer a different path, especially in places with long hours of sunshine. Several prototype systems produced encouraging results. Solar collectors heated the material during the day, driving moisture from its tiny pores. Once it cooled, it was ready to attract water vapor again, creating the next cooling cycle. Instead of depending almost entirely on electricity, these systems used heat that would otherwise go to waste. This approach solved more than one problem. Lower electricity use meant lower operating costs in some situations. Water replaced many conventional refrigerants. Fewer moving parts meant quieter operation and potentially less mechanical wear. On paper, the technology continued to check many important boxes. Researchers didn't stop there. They experimented with different system designs, improved heat exchangers, and tested synthetic forms of zeolite with more consistent properties than natural deposits. Every improvement brought slightly better performance. Every prototype answered one question while creating another. If you're enjoying uncovering forgotten technologies like this, take a moment to subscribe. There are many inventions that almost changed the world, yet somehow disappeared from everyday life. Each one has a story that's far more interesting than most people realize. Even with those improvements, engineers noticed something important. Absorption cooling behaved differently from the air conditioners people already knew. It wasn't designed to blast cold air into a room within minutes. The process worked more gradually, following the natural rhythm of absorption and regeneration, which made careful system design essential. Some projects performed exceptionally well under the right conditions. Buildings with steady cooling demands, abundant sunlight, and enough space for solar collectors often achieved promising efficiency. In those environments, this technology demonstrated that it wasn't simply a scientific curiosity. It could operate in the real world. Success in a demonstration isn't always enough, though. A technology must also be practical to manufacture, install, maintain, and sell. As researchers celebrated technical progress, manufacturers faced a different challenge. They had to compete with an industry that was improving at remarkable speed. Traditional air conditioners became smaller, cheaper, and more reliable almost every year. Mass production reduced costs. Installation became familiar to contractors. Customers already understood how the systems worked. Without realizing it, Zeolite wasn't competing against old technology anymore. It was racing against an industry that was evolving faster than almost anyone expected. And that would change everything. This changing market became the turning point. By the time zeolite cooling was proving itself in research projects, conventional air conditioning had already built a powerful advantage. Manufacturers were producing millions of compressor-based units every year. Costs were falling, performance was improving, customers trusted what they already knew. Here's where many people assumed zeolite failed. It didn't. The science remained solid. The challenge was everything surrounding the science. A good invention doesn't always become a successful product. History is full of technologies that worked but never reached most homes, because they lost a race against something easier to build and easier to sell. Cost was the first obstacle. A zeolite cooling system needed more than the mineral itself. It required carefully designed heat exchangers, absorption chambers, valves and controls that could manage the heating and cooling cycle. Many systems also depended on solar collectors, or another reliable heat source to regenerate the material, which added complexity and increased the initial investment. Speed was the second. People expect an air conditioner to respond almost immediately. They press a button and feel cooler within minutes. Zeolite systems don't work that way. The absorption cycle takes time. The cooling output is steadier, not instant. For many homeowners, that difference mattered more than long-term efficiency. Size added a third complication. Early absorption systems were often larger than conventional air conditioners, with similar cooling capacity. Finding enough space for the equipment wasn't always easy, especially in existing homes. New buildings could be designed around the technology, but replacing an old air conditioner with a zeolite system was far less straightforward. Maintenance mattered too. Although zeolite itself is durable and can last for many years, the complete system still required careful engineering. Every component had to work together efficiently. A poorly designed unit could lose much of the advantage that made absorption cooling attractive in the first place. Then there was the market itself. Air conditioning companies had already invested heavily in compressor technology. Factories, supply chains, installation networks, and technician training were all built around that approach. Improving an existing product was often cheaper than introducing an entirely different one. Businesses usually follow the path with the lowest financial risk, even when another option offers unique benefits. Government policies and energy prices influenced the outcome as well. In many regions, electricity remained affordable enough that consumers focused more on purchase price than lifetime energy savings. Without strong economic incentives, most buyers chose the familiar solution sitting in the showroom. None of this means zeolite had no advantages. In fact, it offered several. It could use waste heat or solar energy. It relied on water instead of many traditional refrigerants. It operated quietly and had fewer moving mechanical parts. Those strengths were real. They simply weren't enough to overcome the momentum of an industry moving in another direction. Timing, not failure, was the real story. Zeolite arrived in a world where compressor technology was becoming cheaper, faster, and deeply established. The better question isn't why zeolite disappeared. It's whether the conditions that pushed it aside still exist today. The answer may be more surprising than you expect. The world that rejected zeolite cooling isn't the same world we live in today. Electricity demand continues to rise. Summers are becoming hotter in many regions. Governments are encouraging cleaner energy solutions. while engineers are once again searching for ways to reduce the environmental impact of cooling our buildings. Suddenly, the strengths of zeolite don't seem so outdated anymore. Modern researchers aren't trying to replace every air conditioner overnight. Instead, they're asking a more practical question. Where does absorption cooling make the most sense? The answer is often places where heat is already available. Large commercial buildings, hospitals, factories, and facilities with solar thermal systems can use that heat to power cooling cycles that would otherwise require much more electricity. Technology has improved as well. Engineers have developed better heat exchangers, smarter control systems, and new synthetic zeolites with more consistent performance. Computer modeling also allows designers to optimize entire cooling systems before they're ever built, reducing many of the problems that limited earlier prototypes. Renewable energy has changed the equation too. Solar panels receive most of the attention, but solar heat is also a valuable resource. During the hottest hours of the day, when cooling demand reaches its peak, the sun provides the thermal energy needed to regenerate the material. That natural partnership makes far more sense today than it did decades ago. Environmental concerns have shifted the conversation as well. Many traditional air conditioning systems rely on refrigerants that must be handled carefully, because some can contribute to climate change if released into the atmosphere. Zeolite cooling uses water as its working fluid, avoiding many of those concerns while reducing dependence on chemical refrigerants. Still, it's worth staying realistic. Zeolite isn't a miracle material. It won't suddenly replace every window unit or central air conditioner. Compressor technology continues to improve, becoming more efficient, quieter, and more affordable each year. For millions of homes, it will likely remain the most practical choice for the foreseeable future. Where zeolite may succeed is in specialized applications. Buildings designed around passive energy systems, remote locations where electricity is limited, industrial sites with abundant waste heat, and solar-powered facilities looking to reduce peak electrical demand. In those settings, the technology offers advantages that conventional systems sometimes struggle to match. Perhaps that's the biggest lesson hidden inside this story. Progress doesn't always move in a straight line. Some ideas arrive before the world is ready for them. Others disappear, only to return when technology, economics, and public priorities begin to change. Zeolite may be one of those ideas. Today, those priorities are starting to shift. As energy becomes more valuable and sustainable design becomes more important, this forgotten technology is quietly finding its way back into research labs and innovative buildings. Maybe the story of zeolite cooling isn't over after all. Maybe we've only reached the end of its first chapter. It never truly disappeared. It simply moved out of the spotlight. While most homeowners forgot about it, researchers continued refining the technology behind the scenes, waiting for the right moment to solve problems that once seemed impossible. That moment may finally be arriving. Around the world, cities are using more electricity for cooling than ever before. As temperatures rise, power grids experience greater strain during the hottest hours of the day. Building more power plants is one solution. Reducing the demand for electricity is another. That's exactly where absorption cooling begins to look attractive again. Modern engineers now see waste heat as a valuable energy source instead of something to throw away. Factories, power stations, and even large data centers produce enormous amounts of heat every day. Normally, much of it escapes into the air. A zeolite cooling system can capture some of that energy and use it to produce cooling instead. The economics changed completely as a result. Decades ago, generating the heat needed to regenerate zeolite often meant burning extra fuel, reducing the system's overall advantage. Today, many buildings already produce excess heat as part of their normal operation. Using energy that would otherwise be wasted makes far more practical sense than creating new energy just to run a cooling cycle. Researchers are also combining zeolite with other technologies instead of asking it to do everything alone. Hybrid cooling systems can switch between conventional compressors and absorption cooling depending on weather conditions, electricity prices, or available solar heat. Each technology handles the job it does best, creating a system that is both flexible and efficient. Artificial intelligence is beginning to play a role as well. Smart building software can predict temperature changes, monitor energy demand, and decide the best time to regenerate the material. Instead of following a fixed schedule, future systems may constantly adjust themselves to maximize efficiency without the homeowner noticing. This reflects a broader change in engineering. The goal is no longer finding one perfect invention that replaces everything else. Instead, engineers combine multiple technologies, allowing each one to compensate for the weaknesses of another. In that future, zeolite doesn't need to defeat the air conditioner. It only needs to make it better. Forgotten technologies deserve another look for exactly this reason. History often remembers the winners while overlooking inventions that were simply ahead of their time. Market conditions, manufacturing costs, and consumer habits can shape the success of a product just as much as the science behind it. Zeolite cooling reminds us that innovation isn't always a straight path. Some discoveries wait decades before the world catches up. Others quietly influence newer technologies without receiving much recognition. What matters isn't whether an idea becomes famous. What matters is whether it continues solving real problems. The next time you hear someone describe an old invention as obsolete, it's worth asking one simple question. Was it truly a failure, or was it waiting for a future that hadn't arrived yet? For zeolite cooling, that future may finally be closer than anyone expected. That leaves us with one final piece of the puzzle. If forgotten technologies can return, how should we judge the inventions we leave behind? The story of zeolite offers an answer that goes far beyond cooling. It changes the way we think about progress itself. We often imagine technology as a straight line. Every new invention replaces an older one, and the past simply fades away. Reality is rarely that simple. Many breakthroughs never disappear because they stop working. They disappear because another option arrives at exactly the right moment, with better marketing, lower costs, or stronger industry support. Zeolite became one of those forgotten ideas. When compressor-based air conditioning spread across homes, businesses, and cities, it created an entire ecosystem. Manufacturers built larger factories. Installers learned one type of system. Suppliers expanded their networks. Customers became familiar with a single solution. Once that cycle was established, introducing a completely different approach became much harder, even if it offered meaningful advantages. History has repeated this pattern many times. Efficient ideas have been overlooked because the world wasn't ready to adopt them. Years later, changing priorities gave those same ideas a second chance. Cleaner fuels, electric vehicles, and passive building designs all gained momentum after technology improved and public needs evolved. Zeolite cooling may be following a similar path. None of this guarantees widespread adoption. Every technology has limitations, and absorption cooling is no exception. Engineers still face challenges involving cost, system size, and performance under different conditions. Research continues because there is still room for improvement. The goal isn't to prove that zeolite is perfect. The goal is to discover where it creates the greatest value. Perhaps that's the most balanced way to view this story. Instead of asking whether one technology should completely replace another, we should ask how different technologies can work together. The future of cooling may not belong to a single invention. It may belong to smart combinations that reduce energy use while keeping buildings comfortable. There's also a broader lesson hiding beneath the engineering. Innovation depends on timing as much as discovery. A brilliant idea introduced too early can struggle for decades. The same idea introduced under different economic conditions can suddenly become practical. That doesn't change science. It changes the world around science. Hold a simple piece of zeolite in your hand, and it doesn't seem remarkable. Yet inside that mineral is a structure capable of moving heat through nothing more than its interaction with water vapor. It's a reminder that nature has already solved many problems engineers continue trying to master. Sometimes the challenge isn't inventing something entirely new. Sometimes it's recognizing the value of something that has been there all along. So why did we stop using zeolite to cool our homes? Not because it was useless, not because the chemistry failed. A faster, cheaper, and more familiar technology took center stage, while zeolite quietly waited in the background. Now, as the world searches for cleaner and more efficient ways to stay cool, that forgotten mineral is beginning to attract attention once again. Its story isn't about failure. It's about timing, persistence, and the possibility that yesterday's overlooked solution could help solve tomorrow's biggest challenges. The next breakthrough might not be brand new. It could be something we forgot. If you enjoyed uncovering the hidden story of zeolite cooling, like this video, subscribe for more forgotten technologies, and share which invention we should investigate next. Thanks for watching, and I'll see you next time.